Hello! In this video, we will explore the concept of a data lakehouse, the layered approach, data modeling guidelines, user access patterns, and best practices for implementation. So let's start with data lakehouse. Data lakehouse refers to an architectural approach that combines features of both data lakes and data warehouses to address some of the limitations associated with these two concepts. A data lake is a centralized repository that allows you to store vast amounts of raw data in its native format at any scale. This data can come from various sources, including structured, semi-structured, and unstructured data. Unlike traditional databases or data warehouses, data lakes store data without the need to structure it beforehand. This flexibility is beneficial for handling diverse data types and sources. A data warehouse is a structured repository for storing and analyzing data. It is optimized for complex queries and data analysis. Data in a warehouse is typically organized in tables and follows a schema. While data warehouses are excellent for analytical processing, they may face challenges when dealing with large volumes of raw, unstructured data. The concept of a data lakehouse emerged as a way to combine the benefits of both data lakes and data warehouses. It aims to provide the scalability and flexibility of data lakes with the structure and performance optimization of data warehouses. In a data lakehouse architecture, raw data is ingested into a data lake and then transformed and organized in a structured manner, similar to a data warehouse. This organized data can be queried and analyzed for business intelligence and reporting purposes. The data lakehouse typically leverages a metadata layer to manage the schema-on-read approach of data lakes, allowing users to define and enforce schema when necessary. Some of the key characteristics of data lakehouse are: 1. Schema evolution. Data lakehouses often support schema evolution, allowing for flexibility and adapting to changes in data structures over time. 2. Unified analytics. A data lakehouse provides a unified platform for both batch and real-time analytics, catering to diverse analytical workloads. Optimized for performance. While maintaining the scalability of data lakes, a data lakehouse is designed to provide better performance for analytical queries compared to traditional data lakes. In a data lakehouse architecture, data is often organized into different layers based on its level of refinement, quality, and usability. The three common layers in data lakehouse are referred to as bronze, silver, and gold. Each layer represents a stage in the data processing and refinement pipeline. Let's explore each layer in detail. Bronze layer. The bronze layer is the raw or landing layer of the data lakehouse. It contains the ingested raw data in its native format without any transformations. Data in the bronze layer is often stored in its most granular and unprocessed form. This layer serves as a reservoir for all types of data, including structured, semi-structured, and unstructured data. While the bronze layer offers maximum flexibility for data exploration, it lacks structure and may contain duplicates, errors, and inconsistencies. Silver layer. The silver layer is an intermediate layer where raw data from the bronze layer undergoes some level of refinement and cleansing. Data in the silver layer is often transformed into a more structured format, and basic data quality checks and cleaning processes may be applied. This layer is characterized by improved quality and a more organized structure compared to the bronze layer. The silver layer acts as a staging area for data that is on its way to becoming more usable for analytical purposes. It also provides a middle ground between the raw data in the bronze layer and the highly refined data in the gold layer. Gold layer. The gold layer represents the highest level of refinement and organization in the data lakehouse. Data in the gold layer is cleansed, enriched, and structured according to a well-defined schema. This layer is optimized for high-performance analytics and is suitable for use in business intelligence, reporting, and other advanced analytics processes. The gold layer may also involve the application of business rules, data governance policies, and additional metadata to ensure data consistency and quality. To summarize, 1. The layered approach, bronze, silver, gold, allows organizations to balance the need for flexibility with the requirement for structured, high-quality data. 2. The layers represent a progression from raw, unprocessed data to refined, high-quality data suitable for business use. 3. Each layer serves a specific purpose in the data processing pipeline, enabling organizations to derive value from their data while maintaining flexibility and scalability. It's important to note that the terminology and specific implementation details of the bronze, silver, and gold layers can vary between different organizations and use cases. The key is to strike a balance between maintaining the flexibility of raw data and providing well-structured, high-quality data for analytics and decision-making. Next, let's delve into the data modeling guidelines across the data layers. Data modeling is a critical aspect of designing a data lakehouse architecture, and different layers, bronze, silver, gold, may require distinct modeling approaches to address specific needs. Here are general data modeling guidelines for each layer. For the bronze layer, 1. Schema flexibility. Embrace schema on read in the bronze layer. Allow for flexibility in terms of data types, structures, and formats in bronze layer. This flexibility accommodates the raw and unstructured nature of the data. 2. Capture metadata. While the data itself may be raw, capturing metadata becomes crucial in the bronze layer. Metadata includes information about data sources, ingestion timestamps, and any other relevant contextual details. For versioning, consider implementing versioning mechanisms to track changes over time in the bronze layer. This ensures that historical versions of records are preserved for audit and analysis purposes. For the silver layer, 1. Structured schema. In the silver layer, start imposing a more structured schema. This involves transforming the data into a more organized format, applying standardized data types, and establishing a basic structure for easier querying. 2. Data quality checks. Implement data quality checks and cleansing processes in silver layer. Identify and handle missing values, duplicates, and inconsistencies. Metadata should include information about the applied transformations. Thorough version control. Continue versioning records as needed in the silver layer, particularly if changes are made during the transformation and cleansing processes. Maintain a balance between historical completeness and storage efficiency. For the gold layer, 1. Defined schema. The gold layer requires a well-defined and optimized schema that is tailored for analytical purposes. This structured schema supports efficient querying and reporting. 2. Data governance. Apply robust data governance practices in the gold layer, including the enforcement of business rules, standardization, and the application of data quality metrics. Metadata becomes even more critical at this stage, providing comprehensive information about the data's lineage and quality. 3. Historical tracking. Implement historical tracking mechanisms in the gold layer to manage changes to records over time. This ensures accurate historical reporting without sacrificing performance. Optimized for performance, structure the data in a way that optimizes analytical performance in the gold layer. Consider indexing, partitioning, and other performance optimization techniques to enhance query speed. Key considerations of data modeling in Lakehouse are: 1. Evolutionary approach. The transition from bronze to silver to gold should be seen as an evolutionary process. Each layer builds upon the previous one, adding more structure and refinement. 2. Metadata management across all layers. Robust metadata management is crucial for providing context, lineage information, and ensuring data quality. 3. Balancing flexibility and structure. Striking the right balance between schema, flexibility, and structure is key, ensuring that the data remains adaptable to changes while meeting analytical requirements. It's important to note that these guidelines are general recommendations, and the specific requirements for each layer may vary based on the organization's goals, industry regulations, and the nature of the data being processed. Data modeling should always align with the broader data strategy and business objectives. Next, we delve into user access patterns. User access patterns refer to how users interact with and query data within each layer of a data lakehouse. The access patterns are influenced by the characteristics and purposes of each layer. Here are the typical user access patterns for the bronze, silver, and gold layers. For the bronze layer, 1. Exploratory analysis. Data scientists, analysts, and data engineers often access the bronze layer for exploratory analysis. They might perform ad hoc queries to understand the raw data, identify patterns, and assess the overall quality. 2. Raw data exploration. Users in the bronze layer may explore the raw data to gain insights into its variety and structure. This can involve querying semi-structured or unstructured data directly. 3. Schema discovery. Since the bronze layer allows for schema flexibility, users might dynamically discover the structure of the data as part of their analysis. For data ingestion monitoring, operations teams may access the bronze layer to monitor the status of data ingestion processes and validate that new data is arriving as expected. For the silver layer, 1. Data transformation. Analysts and data engineers often access the silver layer to work with data that has undergone some level of transformation. This may include querying cleaned and partially structured data. 2. Quality assurance. Users in the silver layer may focus on data quality assurance, running queries to identify and address any issues introduced during the data transformation processes. Through preliminary analysis, data scientists and analysts may perform preliminary analysis in the silver layer to assess the quality of the data and its suitability for more advanced analytics. 4. Transformation monitoring. Operations teams may monitor the status and performance of data transformation processes in the silver layer. For the gold layer, 1. Analytical queries. The gold layer is optimized for analytical queries and is the primary source for business intelligence and reporting. Users, including business analysts and decision makers, perform queries to derive insights and make data-driven decisions. 2. Structured analytics. Users in the gold layer work with well-structured and highly organized data for in-depth analysis. This may involve complex queries, aggregations, and reporting. Historical analysis. The gold layer is a key source for historical analysis, allowing users to analyze changes over time with the help of sophisticated historical tracking mechanisms. 4. Dashboard and reporting. Business intelligence tools and reporting platforms typically connect to the gold layer to generate dashboards and reports for decision makers. Key considerations when designing user access to Data Lakehouse are: 1. Data accessibility. Each layer provides a different level of data accessibility and refinement. Users should choose the appropriate layer based on the nature of their analysis and the required level of data processing. 2. Performance. Users accessing the gold layer can expect optimized performance for analytical queries. The gold layer is designed for efficient querying and reporting, whereas the bronze and silver layers may offer more flexibility at the expense of performance. 3. Data lineage. Users across all layers may need access to metadata and data lineage information to understand the origin and transformation history of the data. These user access patterns are general guidelines, and the specific patterns may vary based on organizational requirements, the nature of the data, and the roles of users within the data ecosystem. Implementing a data lakehouse requires careful planning, consideration of best practices, and adherence to key principles to ensure the success of the architecture. Here are some best practices for implementing a data lakehouse. Define clear objectives. Clearly define the objectives and goals of implementing a data lakehouse. Understand the specific business requirements, analytics needs, and desired outcomes. Align the implementation with broader organizational objectives. Understand data governance. Establish robust data governance practices. Define data ownership, access controls, and data quality standards. Implement policies for data lineage, metadata management, and compliance with regulatory requirements. Design the architecture to accommodate both raw, unstructured data and highly refined, structured data. Implement data lakehouse layers. Follow the bronze, silver, and gold layer approach for organizing and processing data. Leverage the strengths of each layer to provide flexibility, quality, and performance optimization as data progresses through the pipeline. Metadata management. Prioritize metadata management. Capture comprehensive metadata for all data layers. Metadata should include information about data sources, transformations, lineage, and quality metrics. It is essential for data discovery and understanding. Versioning and historical tracking. Implement versioning mechanisms, especially in the bronze and silver layers, to track changes over time. Use historical tracking techniques such as slowly changing dimensions to manage changes to records while maintaining historical context. Performance optimization. Optimize performance in the gold layer for analytical queries. Consider indexing, partitioning, and other performance-enhancing techniques. Ensure that the data is organized to support efficient analytical processing. Security measures. Prioritize data security. Implement encryption for data at rest and in transit. Establish access controls to restrict user permissions based on roles and responsibilities. Regularly audit and monitor user access to sensitive data. Monitoring and operations implement monitoring and alerting mechanisms to track the health and performance of data processes across all layers. Monitor data quality, transformation processes, and data ingestion. Establish proper logging for troubleshooting. User training and adoption. Invest in user training and adoption programs. Ensure that users understand the architecture, tools, and best practices. Foster a data-driven culture within the organization to encourage effective use of the data lakehouse. Scalability and flexibility. Design the data lakehouse to be scalable to accommodate growing data volumes. Leverage cloud services for scalability. Consider the future data needs of the organization and plan for flexibility in adapting to evolving technologies. Collaboration between teams. Foster collaboration between data engineering, data science, analytics, data governance, security, operations, and business teams. Encourage cross-functional communication to ensure that the data lakehouse meets the needs of various stakeholders. Continuous improvement. Treat the implementation of a data lakehouse as an iterative process. Continuously evaluate and improve the architecture based on user feedback, evolving business requirements, and advancements in technology. Remember that the implementation of a data lakehouse is not a one-size-fits-all solution. Tailor the architecture and practices to the specific needs and characteristics of your organization. Regularly assess the effectiveness of the implementation and make adjustments as necessary to ensure ongoing success. Overall, this video aimed to provide a comprehensive understanding of data lakehouse concepts, modeling guidelines, and implementation best practices.